Fred Demoli from UTBM. Actually, he's kindly hosting me at the moment, so I'm talking to you from France at UTBM. So Frederic is going to talk about the challenges in design for 4D printing, and we are very interested to hear more about these challenges and how Frederic and his team tackled these challenges. Frederic, the floor is yours. Go ahead and.
Yeah, thank you, Madi. Hi, everyone. Can you see my screen?
Yes, we can.
Okay, great. So I'm a professor at Belfort-Montbéliard University of Technology in France. I am also a member of the University Institute of France. And I will, first of all, thank all the collaborators I have and also all the co-workers that make the research possible. It's a great achievement. I will also thank all the financial support, so most of them come from French agency. So, sorry. Before presenting my vision of design for 4D printing, I think it's relevant to highlight the industrial and scientific stakes, whether at the national or regional side, where specific expectations are dedicated to advanced material and processes, integrated intelligent system, programmable matter, and material by design. If I go through the international level, such as in Europe or US, for example, attention is focused on augmenting product functionality, making system intelligent for configuration purposes, or even developing physical product and digital twin, all in the broader Industry 5.0 initiative, where additive manufacturing and soft robotics can play a great role. So at this level, you know, ESA, NASA, NSF, or even Horizon Europe is now aware about this kind of smart system. I've also introduced a Gartner Ape Cycle made in 2018, where you can see that 4D printing is part of the innovation trigger. So 5 years later, we can say that this technology now entered the peak of inflated expectation stage. So this means that we have a lot of pressure to demonstrate that 4D printing is useful for industry with, let's say, innovative application. So for all this reason, my research group and I are currently developing advanced design methods and digital threads with advanced fabrication techniques for original shape-changing mechanism in a way to create transformable system compatible to human usage environment. So additive manufacturing is the first pillar of 4D printing. So this technology is nearly 40 years old, where the first patent was a French one, introduced by Jean-Claude André, a friend of mine from University of Lorraine. So with this technology, complexity is free in terms of shape, functionality, hierarchy, and materials. There are, let's say, 2K articles with a growth of 14, with a publication rate of 14% a year, and the research now is like incremental. And 4D printings introduced 10 years ago by Tibbets, Dunn, and Key had a new kind of complexity since we integrate smart material with energy stimuli. So the complexity is augmented. They are, let's say, 2.5K articles with a production rate of 44% a year. And the research is interdisciplinary and disruptive. So it is interesting also to, let's say, represent the history of, or let's say, the evolution of system where design have been focused. So over the last decades, design methods have been focused on mechanical system, mechatronic system, connected object, and cyber physical system. Now the trend is towards smart system. If you check the capability maturity model, okay, the three main systems are more or less mature through level 5 and 4, and for smart system, all research are still made at the laboratory stage, so from a design point of view, it is like ad hoc. What is interesting that industry is starting more and more to investigate 4D printing, or let's say shape-changing systems. You can see BMW has developed in 2016 a concept car that has, let's say, shape-changing body or even deployable cockpit. We can see Hankook with that describe, or let's say that develop shape-changing tires. We can see Adidas with 4D shoes or even stands. So the smart system of the future should be adaptive, reconfigurable, deployable, and transformable. If I have a look on most of the effort in 4D printing, I can highlight two different strategies. The first one is a single material deposition, which means that you will use a 3D printer with only smart material. And the idea to tune the shape changing is to control the printing part, or let's say the light irradiation amplitude. And by considering these both parameters, you can generate a lot various shape changing primitives. The picture I present here come from Georgia Tech, MIT, and Harvard. And they use DAW, they use FFF, they use as well TLP to produce these single material objects. Another strategy is to consider heterogeneous or multi-material 4D printing and metamaterial. If you check the literature, you will see the various material distribution from sandwich, bilayer, spatial pattern, gradient, or even digital structure. I give just an example here on the left side about spatial pattern, and on the right side, the digital patterns. The idea is to compute specific algorithm like genetic algorithm, and to provide a support in design in a way to target a shape change. So the idea is to compute counterintuitive distribution, then can achieve this target. I think before talking about design, it is relevant to have an overview about the mechanical performance of 4D printing actuators. So I draw here the main smart material categories from SMP, SME, piezoelectric, hydrogel, EPMC, liquid crystal elastomer. I try to compare with metal. And the idea is to highlight that the new model should be increased. The response time is still high, so we need to decrease this kind of parameter, and we need to strongly improve the force generated as the efficiency of these actuators. From a additive manufacturing point of view, I think, or even from a material elaboration point of view, what is hard for us is to find the shell shape smart materials. So we need to formulate, we need to tune specific material for specific application, and smart material require improvement due to their functional fatigues. They have also multiple scale behaviors that need to be considered. And from a additive manufacturing process, I think it would be interesting to increase material process couplings, or let's say multi-material capacity. And the last one is probably the third pillar of 4D printing is the stimulation. So stimulation today in most of the research is considered from a global application point of view, an external way. So the idea is to how to provide the stimulus in the right location at the right time. So the stimulator volume and energy consumption are also challenging. So in order to build a design perspective, so how main target is to design smart systems that make sense, it meets use. And if you want to keep this target in mind, we have to consider several 4D printing facets, like multi-material from resin, filament, fiber, powder, pellet, to cover polymer, metal, ceramics, both those materials. We have to consider multiple domain, material chemistry, physics, manufacturing, robotics, multiple additive manufacturing techniques, multiple physics and energy. We are also to consider different scale, different temporality, even different function for design, even multiple worlds. So most of the effort have been done on the digital and physical world. It would be interesting to address cyber or even social due to the new kind of interaction between human and material. And to leverage this facet from a design perspective, we have to develop knowledge, models, methods, and tools, which can include geometric optimization, multiple representation, symbolic AI reasoning with semantic and ontology, connectionist AI reasoning with machine learning, deep neural network, or even biomimetic computing. And the last part is also the application sector. So to my knowledge, interested application sector are medtech, automotive, textiles, aerospace, space, photonics. So to sum up, the big issue is to design, to consider at the same time design for material assembly, design for additive manufacturing, design with stimuli, design with smart material, design for transformation, design with artificial intelligence, and design for performance to reach application. So our first effort were dedicated to the development of an ontology for 4D printing knowledge and reuse. So this ontology is built upon theories called 3D-dimensionalism or even 4D-dimensionalism. We have built our ontology on basic formal ontology, and the ontology is used to capture all the knowledge from product architect, material expert, product designer, process planner, the knowledge from material database, IM standard, ad hoc experiments. And the idea is to capture the knowledge and for reuse purposes. So one, I describe here a part of the ontology. The ontology is similar to knowledge graph. You can see a blue circle that represents a part of the knowledge classes. You will see in purple circle the instance, which means the knowledge from physical experiment or simulations. And you will see that all the classes are connected with the semantics that provides an appropriate explainable reasoning. So based on this ontology, we initially developed a recommendation mechanism for material distribution. And this first recommendation mechanism is based on semantic simulative vector space model, which means that for specific design application, the designer may introduce some target vectors in terms of word, and this target vector will be compared with what we have in the database, and the system is able to find the most similar experiment found in literature that may fit with a specific application. So we implement this kind of mechanism for material distribution, and let's say a couple of months later, ChatGPT appears. So which means that we have to extend this kind of approach to large language model now. We also develop simulation methods in order to provide to the designer very quick results. So we apply a voxel-based modeling in order to have qualitative result of shape changing behavior. So with this kind of modeling scheme, we have developed an add-on in a Grasshopper with we know a Grasshopper environment called VoxSmart. So this tool is able to build any kind of geometries and discretize the geometry in terms of voxel. So you can control the size of the voxel. Probably you can put the size of the voxel here. Once voxelized, we can allocate specific material property to specific region of the geometry, and then you can simulate very quickly the results. So this tool provides a first feedback for the designer, and we also implement genetic algorithm in order to address inverse design problems. So for any designer, the main issue in 4D printing is you have an idea about the initial stage, you want to achieve a design target shape change. And the idea with this kind of reasoning is to find the appropriate distribution of active and passive material. We try to add much more complexity in the reasoning. In this kind of framework, we have integrated a void into the structure. So the main idea is if we are able to reduce the amount of smart material, probably we will need less energy as stimulus. So the idea is to target the same shape change by, let's say, playing or distributing active material, passive material, and void. So we develop a specific Python code within Abacus to run the simulation. So we have made some progress, with the new original design tool with computational power. So which means that we are able to combine any kind of material together, even dissimilar material. So now we are faced with additive manufacturing limitation, and to overcome this kind of multi-material capacity, we develop some, let's say, customized the idea is to combine multiple DIW.
Hi, Madi.
Yes, I think
There has been a
his
little bit
connection
of
is a bit, yeah, his connection is a bit weak. Frederic, are you with us?
Yeah, I can see Frederic, you're back.
Sorry, can you see my screen?
Yes. Carry
Sorry.
on, please.
Okay.
So the first strategy is also we are trying to investigate is robotic assembly. The idea is to combine voxel or polyvoxel, or also called polycube, together and stack them into built 3D printing structure. We have also another technology that. So from the left to the right, you will see that the material composition capability will be increased in terms of, let's say, dissimilar material, which means, for example, for the robotic assembly, we will be able to combine. So for the multi-head DIW, we built, let's say, a couple of years ago, on the CNC machine, a customer has a barrel DIW machine, which means that the barrel is able to rotate, to shift from one material to another, and we integrate also UV light, to cool the resin. We develop our own slicer within Grasshopper in our environments. As for the second strategy, we decide to put on the same gantry a gripper, DIW head, FFF heads, and also UV curing system. So we use an open source 3D printer, which is iRate 3D. We combine with OmniQS 2000, and we had a lot of printing head on the same gantry in order to build original object with multiple material inside. But this kind of machine provide a lot of complexity in terms of determining the appropriate printing parameters. So we decide to leverage digital twin technology to accelerate the determination of the printing parameters. Here is an example of the interface we built in the Rhino Grasshopper environment. So for each socket of the 3D printer, we will define the appropriate printing head with the appropriate parameters. We are able to build the G code for each head, and we develop Python code in order to concatenate J code together. The digital twin here is also composed of camera that are being integrated into the machine in order to capture data, or let's say image from each side of the parts. And the idea is to use digital image correlation in order to have, let's say, closed loop feedback and reasoning in order to determine in a single run the appropriate process parameter. For the robotic assembly, we introduced a topologically interlocking voxel assembly, which means that starting from our design tool, that computes a voxel-based multimaterial structure, we, let's say, have developed numerous steps for digital material partitioning with blocking relation modeling, interlocking polyvoxel assembly computation, and then assembly planning. So if I try to apply this to a specific beam with specific material distribution, the idea is to extract homogeneous subassembly that develop the fixed interlocking blocks with key interlocking blocks. So key interlocking blocks means is similar to fasteners, and then assembly sequence. So through the first experiment, so the target shape changing is defined in our design tool. We print it separately, so which means that we use as active material thermal-responsive hydrogel blocks, print with DLP. We print passive elastomer blocks with polyjets, and we manually assemble all the parts together in order to produce a shape change through thermal stimulation, which means that once temperature reach, let's say, 40 degrees C, we will have a new shape. So regarding my design roadmap, so I describe here what we have done from a knowledge point of view, model, method, processes, and tools and equipment. And what we have achieved today represented in blue, which means the work has been published and funded. We're also working on large language model, 4D printing data representation for AR purposes. We're working on smart material distribution pattern, metamaterial pattern discovery. We are working with prediction, with machine learning. We are currently improving our digital twin. And for the future, we plan to extend what we have done with the knowledge at the object level to the system or material levels. We are planning to augment the model complexity in terms of geometry, structure, even in terms of multiphysics complexity. We are planning to increase our computational power with by combining, let's say, forward prediction with machine learning, biometric computing, and symbolic AI reasoning in the case of neuro-symbolic integration. And from a 4D printing point of view, in terms of tools and machine, we are currently working on covering multiple scales and combining these scales in the same structure. This is my last slide. So the 4D printing society is a young society. I'm trying to contribute in order to reinforce this society from the French, from a French initiative. So I'm currently PI of a large-scale research project called Artemis. So this project means accelerated discovery and development of smart material and structure with 4D printing society. So this project, in this project, we have 2 additional partners like Polytechnic in Paris and University of Montpellier. We have received, let's say, 1.5 million euros over 48 months. So the idea is twofold: explore and discover smart material, especially SMP, LCE, SMA, and hydrogel composition, and also explore and discover 4D printing structures in terms of material distribution. I mean, symbolic AI with machine learning, conditioning AI. I'm also co-author of 2 books on 4D printings, published in 2022 with my friend Jean-Claude André, published with Wiley. I'm also, I'm currently proposing a special interest group in France, funded by the CNRS on smart matter transformation in 4D printing, where I'm trying to gather.
Frederic, you are on mute. You are on mute. I think you are muted. Yeah, okay.
for your availability. And okay, I'm available for question. I will try to.
Okay, thank you so much, Frederic, for sharing your great achievements. Thank you so much. Frederic, can you hear me?